In the last video, we did a couple of examples together, and I forced you to draw all of the possible products that could exist with an elimination reaction. And then I forced you to convert that over into structures that look like this, that showed a little bit of the stereochemistry. So the clear trans notation, and then look at the substituted groups. How many groups are on the carbons, and then compare that to your other option, and then look at delocalization to see if that plays a factor of anything, and then that is what we'll use to make our judgment call about which one is a major product and which one is not. Folks, I did this for a reason, and that's because when we talk about elimination, and what we've done up to this point are E2s. Never really mentioned that, and I did that for a reason. I didn't want you to get confused and bogged down with that information. But what we have done so far have all been E2s. Notice we've erased the halogen at that carbon, and that carbon is the one that gets the double bond, either to the left or to the right of it, depending on what kind of molecule it's involved in. So in E2 reactions, we need to make a summary now. And that summary looks like this. So if we have an E2 where we're solely focused on the carbon that did have the halogen group in the beginning, look at this. Here's the bromine, and then right up here is the carbon that's on that bromine. That's the alpha carbon. If that alpha carbon is tertiary, or if that alkyl carbon, alpha carbon, is secondary, or if that alpha carbon is primary, we can use that as a judgment call to figure out a little bit of relative reactivity. The more stable that these are, the more willing they will be to react in order to form that double bond. Which means, if this bromine leaves, and I do not get anything on in its place, and we create a double bond with this alpha carbon, no rearrangement, that alpha carbon, if it's tertiary, folks, in this double bond orientation, we got a substituent and another substituent and another substituent at least. Now you compare that to the secondary. If this bromine is eliminated, we have an alpha carbon. That alpha carbon forms a double bond. Over on the right-hand side, though, we just have one group. That's it. And over on the left-hand side, we only have one group. There's less groups, so therefore it's less stable, which therefore it means it won't react as fast. We've already been doing this. This is what I've been making you do. You just didn't realize it. In order to figure out which product is the most stable, we have to look at the groups that are on that double bond, on those sp2 carbons. The more of them, the better. The more of them, not only the better as far as stability goes, but the more willing that molecule will be to react in order to give me that product, so the reaction happens faster. Okay? And then finally, the primaries over here at the end, this bromine's going to leave. Well, the carbon's going to involve a double bond, but over on the right-hand side, look, there's only two hydrogens that are there. We don't really count those as groups at all, and we only have one group. So a primary alkyl halide gives me a primary substituent, just one. A secondary alkyl halide gives me secondary substituents, 2. And a tertiary alkyl halide ends up giving me 3 alkyl substituents, which is the most stable out of the bunch. So in E2, tertiaries react faster than secondaries, which react faster than primaries. Another way to keep this in mind, don't even bother, folks, with the double bonds. If this bromine decides to leave, what we have created is a tertiary carbocation before the double bond exists. We know that tertiaries, as far as carbocations go, are the most stable. That rule doesn't change here either. So because it's more stable, this will form a more stable product. It could be as simple as that if it needs to. So with E2s, just like it's written on the screen, tertiaries are much better than secondaries, which are much better than primaries. We also need to pay attention to steric hindrance. And steric hindrance is something that I've been kind of hitting at in the past over and over. Here we have a bromine group, and this bromine needs to get eliminated, right? Okay, well, if this bromine gets eliminated, well, we've got a couple of options here. We can form the double bond to the left, and that's what we've done here. Or we can form the double bond on the right-hand side, which is what we've done here. So here's option number 1, and here's option number 2. Well, let's say that we use a strong base. I mean, this is pretty strong, right? There's a negative on it, so we would look at that and say, strong base. Okay. The problem, though, is that we call this a very bulky base. I mean, this thing is beautiful. It is attractive. But it's also fairly large, which is okay, right? This group is going to try to go in and pull off or persuade that carbon to knock off bromine. Well, it can't get in there. Look, bromine's or that carbon's surrounded by buddies. So just like before with the eliminations, that carbon's going to go, oh, this bromine's got to go. You're off. You're out in the street. I'm single. I'm going to be single for a while. I don't need a relationship. Leave me alone. Smack. And then the bulky base will go to a buddy. Which buddy will it go to? The one that's more convenient. That's the one it's going to go to. So if it gets to buddy on the left, it's pretty accessible, right? I mean, it's sticking out here on his own, just minding his own business, having a good time, drinking at the bar, listening to the music, and then bam, a bulky base comes in. Well, it's not going to leave that carbon alone until it gets a drink and goes. So it rips a hydrogen off. Okay. The same story happens up here with this methyl group. Bulky base comes in, up here at the top. I'm not going to leave you alone till you buy me a drink. Okay, here you go. Bye-bye. Off you go. Shoo, fly, shoo. So it takes a hydrogen and it leaves. Those are actually the same case scenario, which is why we don't really do 3 products, because if the double bond happens between that methyl group, it's the same thing as if it happens with that methyl group. So option number 1 exists. There you go. Notice this is the major product. 72% of the time, that one's going to happen. How do we know 72? You can't calculate that. I'm never going to ask that. But that is the major product. Now let's talk about why that's major. Because it looks to me like if we wanted to compare the substituted groups, look at this option. Carbon, double bond carbon. There's my legs. That carbon has a methyl and a methyl. And this carbon to the right has a hydrogen and a methyl group. 3 substituents there, right? Now let's look at the one over to the right-hand side. C, double bond C, leg, 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 leg. This carbon to the left, 2 hydrogens. The carbon to the right, we have a methyl group, and we have an ethyl group. This one only has 2 substituents, right there. Ethyl, methyl. This one has 3. Normally, you would say, hey, 3 substituents, so therefore this is the major product, and I would go, wrong. That's wrong. It's not right. Not in this case either. And you're going to look and say, well, you told me only delocalization. Well, no, that was one of the exceptions. Delocalization does trump those number of substituents on the double bond. But there's also something else that's at play here. And that is the size of the friend that showed up to the bar looking for a man or a woman. Okay, well, what do you mean by that? This is a bulky base. This bulky base has easy access to that friend and that friend. They're on the end, folks. They're on the end. This friend, though, is in a seat at the bar surrounded by other people. It's much easier to go over to the buddy that's at the very end of the bar stool and talk to them versus trying to weasel yourself into this molecule on the inside, because this is a very bulky base. And trying to get in there and squeeze in between all those bar stools and try to get into that beta carbon will be very difficult for a bulky base. And we call that steric hindrance. So the reason that option number 1 here is the major product is because we have a bulky base, like a tert butoxide, that needs to go in and rip a hydrogen off. And this is fairly large. And it can't easily do that onto an interior carbon like this. The more exposed that those friends are on the outside of the bar stools, the better this bulky base feels about going in and asking for a drink. And that's why option number 1 is the major product. We only have to do that with bulky bases, though. Everything that we've used so far has pretty much, for the most part, been very tiny, been very petite. And they can go in there and do that a little bit easier. But the big bulky ones cannot. So steric hindrance does play a factor. We don't see a lot of these that are happening in the example problems and stuff. They actually behave themselves when it comes to this example. But they will give it to you every now and then, and you just got to be prepared for that. It's almost like a trick question when they do it. Okay? All right, so let's do an example problem. It says, give the major product obtained from the E2 reaction. Remember, that's what we've been doing this whole time. With OH. OH is pretty petite, little, very strong, very attractive. Of the following molecules. And how is it different than the SN2 products? And the reason they say SN2 is because, folks, this is an OH group, and that's a strong nucleophile, and it promotes SN2 whenever they can happen. So let's take a look at number 1. Let's focus on elimination first, and then we'll go through and do substituted products. This chlorine, and I'm just going to redraw it. There we go. So in elimination, we're going to erase the chlorine, erase the bond that happened, and we're going to draw a double bond. The question, does it go left or does it go right? And you're going to tell me it goes right-handed. Because if it goes right-handed, you get more groups on the carbons of those double bonds. More substituted. So in this case, we have a methyl on the left, and over here, we have a methyl on the right. In the other version, we had hydrogens, and that was it, just on one of the carbons. More substituted, more stable. There is the E2 product from this reaction. Now let's take a look to the one on the right. I'm going to redraw it. Go there. Well, if this is elimination, because they tell me, I'm going to eliminate the halogen, I'm going to eliminate that bond, and I'm going to have to draw a double bond somewhere. Do I go left or do I go right? And you're going to tell me you go right-handed. Why? Double, single, double cause you trouble. This is now becoming a delocalized network system, which is very important in the stability of a molecule. So this is the E2 product that's major when the elimination decides to happen, because delocalization is now actually in play. Let's take a look at this BR. So with this BR group, again, I'm going to draw the ring, a double bond there, and a bromine is here. So in the first part of the problem, E2 happens. All right, so bromine goes away, bond goes away, and I need to draw a double bond in here somewhere. Well, do I go left or do I go right with it? There's an option there. Where do you put it to get the major product? I hope you're going to tell me on the right-hand side. And the reason is just as before. Delocalization. Right there. Double, single, double caused it trouble. There you go. Delocalization's now at play. It improves the stability, and that is my E2 product. Finally, this one over here, as before, I'm going to redraw. There we go. And now it wants me to go in and do an E2. All right, so I'll eliminate the chlorine, I'll eliminate the bond, and I've got to figure out where I draw the double bond. So do I go left or do I go right? And the answer is left. And the reason I do it there is because this carbon now has two substituted groups, a methyl and a methyl, and this carbon has one. That's an ethyl group. If I went to the other side, folks, I would not get that. I would get one group on the left and one group on the right, and that would be it. If you don't believe me, draw that option and compare the two like we've done before. So that is the product of the E2 reaction. Now, that's not all of the question, because it says, how would it be different than SN2 products? Okay, so let's kind of do that as an option, SN2 here. Again, I'm going to redraw. There we go. And this chlorine is attached to a carbon that is secondary. So we know SN2 or SN1 happens. This is a strong base, so it promotes SN2, which means that wherever that chlorine is at, that is where my nucleophile will go. So there, in this case, we have made an alcohol. In the other case, we made an alkene. That's how the SN2 product would be different than the E2 product. They don't give me anything about stereochemistry. I don't know anything about R and S's, so I just leave that off of the product as well. All right. Now let's take a look at this one over here. I'll do the same thing, double bond, and chlorine there. That's also a secondary, which means SN2 or SN1 can happen. It's a strong base, so SN2 is preferred, which means that that chlorine is going to go away, and that carbon is going to substitute it with an OH group at that spot. That's all you got to do with it, folks. Did you realize that SN2 was that easy back then? If not, now you know. That's all you got to do. And if this was easier to you than what it was in the past lecture module, guess what, folks? You're learning. And that's what we're here to do. Down here in option number 3, we'll do another ring system with a bromine there and a double bond that's here. I know, that's sloppy. Shame on me. Look at that. So this bromine is on a secondary carbon. That secondary carbon's SN2 or SN1. Strong OHs make SN2s happen preferred, so bromine's going to go away, and then on that is going to go an OH. And that is the SN2 product. Again, another alcohol. But was it that hard? I hope not. And then finally, over here in our last example, and then here we get a chlorine, and there we've got a methyl group. What do you think I'm going to say? Secondary carbon. Secondaries, SN2 or SN1. OH is a strong nucleophile that promotes SN2. So wherever the chlorine goes, that is where the OH is going to go and end up. And that is the SN2 product if that route decided to go forward. So folks, hopefully those example problems allow you to feel more comfortable with elimination, but also more comfortable with substitution. I also need you prepared to go in and name these, because we can do that, right? This E2, if I go up here to the top and do option number 1. This E2 is a 1, 2, 3, 4. That's a butene, and that double bond happens at carbon 2. So my other option, 1, 2, 3, 4, is a butane, and that's on carbon 2. So 2-butanol. So with 2-chlorobutane, if 2-chlorobutane undergoes elimination bimolecular, I will get 2-butene as a product that will preferably be in the trans position. If 2-chlorobutane undergoes a nucleophilic substitution bimolecular reaction, otherwise known as SN2, then we're going to end up getting 2-butanol as a product. That 2-butanol will have the reverse stereochemistry of the original. However, I cannot confirm or deny what that stereochemistry is because the starting reagent did not give me any information on that topic. That was a mouthful, wasn't it? Let's look at my next one. How do we name this starting reagent? 1, 2, 3, 4, 5. So this is a pentane. But actually it's a pentene because of the double bond, and it happens at spot 1. And then 1, 2, 3, 4 down, we have a chloro group. 4-chloro-1-pentene. Well, what if we had to name that E2 product? 1, 2, 3, 4, 5. This is a penta, but it's a diene because there's 2 double bonds. And that diene happens at spot 1, 2, and 3. 1,3-pentadiene. And then the SN2 product, well, there we go. OH actually takes priority. That's something that was off of that chart that I told you to always keep. So because of that, I'm going to name it as an alcohol and forget about everything else right now. So 1, 2, 3, 4, 5. So this is a pentane. Drop the E, add all, pentanol. And this is a 2-pentanol. However, the problem is that a double bond is also there. So I'm going to have to slightly modify this a little bit. OH gets priority. That's spot 2, it's 3, and then 4. So this is a 4-pentan 2-all. Again, all of this stuff wrapped up into a problem. So if 4-chloro-1-pentene undergoes an elimination bimolecular reaction, I will end up getting 1,3-pentadiene as a product, preferably with all double bonds in the trans location. And then if 4-chloro-1-pentene reacts with a nucleophilic substitution bimolecular reaction, I will end up getting 4-pentan 2-all as a product, and a reverse stereochemistry will happen. Once more, I cannot comment on the stereochemistry because it doesn't tell me what it is. If this was shaded, then I would draw this one with a dashed wedge. That's how I would show that in the product reaction scheme. So, hopefully you feel a little bit better about elimination. Hopefully you feel much better about substitution at this point because we're seeing it more and more. But we haven't really talked about the other form of elimination yet. We've only been focused on E2. Everything that we've done, we've focused on E2. No rearrangement. That carbon has a halogen, that halogen leaves, and that carbon either goes left-handed or right-handed with the double bond, one or the other. So how does E1 differ? What do we need to watch out for? Very similar to substitution, it's rearrangement. So in the next video, we're going to talk about E1. We're going to kind of work with those products and see what rearranges and why it rearranges, and compare those to the E2 products. And then we're going to have to make a decision on how do we know which route goes forward, just like with substitution. How do we know if it's E2 or how do we know if it's E1? That's what we're building up to. So in the next video, this is where we're picking up, and be ready to discuss E1 elimination reactions.